reactions. If that anomeric carbon is free, what do I mean by free? See that on the OH, this one is, what form is this? Is this alpha or beta? Alpha, okay, so we have an alpha D-glucose here. And if, it doesn't matter if it's alpha or beta, but if you look at the oxygen, the OH, that is on the carbon number 1, or the anomeric carbon, that's in the carbon number 1, the anomeric carbon, and you see an OH on it, and you see the H on it, that means it's a free sugar. It's not in an anomeric bond, a glycosidic bond. So if that is free, then we can say it's a reducing sugar. What happens is that there's a reaction that's going on here. What is happening to this carbon number 1 from here to here? This structure to this structure. Double bonds forming. So what does that mean to this structure, to this carbon? Is it being oxidized or reduced? Oxidized, right? So what's happening, since we have a hydrogen on the oxygen, this carbon can be oxidized. And because this can be oxidized, you don't just have an oxidation. You have to have a reduction with an oxidation. So what it's going to do is it's going to reduce the silver on this complex. And when it reduces it, it goes from silver on a +1 charge to silver 0. Well, that's metal, just solid metal. So what you see is make a silver mirror on your test tube. Did anybody ever do this in a biochem or a biology lab to see if you have a reducing sugar?
We did a different test.
Did you did the other test?
Yeah, that's what the Benedict's one.
Yeah.
Sounds more interesting.
So this is really important that we can identify which anomeric carbon is free, which is not in a glycosidic bond. We're going to talk about glycosidic bonds in one moment. Not the first carbon, the anomeric carbon, because if it was a ketose, then the double bond would be here. And so if it's a ketose, then the double bond would be on the second carbon. And so if it's on the second carbon, then there will be another carbon on there. I'll point that out in a moment. So if it's involved in what we say a glycosidic linkage, there will be a negative tolerance test reagent. If another anomeric carbon is free, there'll be a positive tolerance test. And the positive is that you'll see a silver mirror because the silver ion is going to go from a silver ion to silver metal. Okay. Now, so they can be oxidized. When we oxidize the top carbon, then we call it an aldonic acid. When we oxidize the bottom carbon to an acid, we get a uronic acid. So top is aldonic, bottom is uronic, and both is alderic. That's just some definitions. So let's go over that again. So we have, so here we have glucose, and what we've done is this is normally the aldehyde in carbon number 1. So what we've done is we've made it an acid. So that's an oxidation, going from an aldehyde to an acid. So where we go, we call it an aldonic acid. When we've taken a monosaccharide and oxidized the top carbon, carbon number 1. When we've oxidized the terminal carbon, carbon number 6, it's called a uronic acid. And when both the top and the bottom, the aldehyde and the carbon, the terminal alcohol has been oxidized, then that's alderic. So there's some definition words that you need to know. We can also reduce them. And one of the most important reductions is where we've taken out an OH on this carbon number 2 on ribose. Remember, ribose is an aldopentose And there's got to be an OH on the on every single carbon, and except for the one that's an aldehyde. So here we've seen that we've gotten rid of the OH here. So that's why we call it deoxyribose in DNA. We've gotten rid of, we've reduced an alcohol to just a hydrocarbon. And if you're chewing gum right now, then you probably can look on the ingredients and find sorbitol or xylitol as the non-sugar sweetener in your sugar, in your gum. So that's something we do. And so that by reducing that aldehyde, what we've done to an alcohol, it keeps the sweet taste to it, but it's not a sugar anymore. And so we've reduced those carbon number ones. Okay, what we're going to see, so we can oxidize, we can reduce these sugars, and we can actually add groups to it. So one of the first reactions, the first reaction that happens to a glucose when it enters the cell is that we pop a phosphate onto it. Requires energy. What we're going to do is break up an ATP, which is it's our energy currency. That holds free energy. And so what we're going to do is we're going to have a nucleophilic substitution where we're going to create a single bond between the oxygen of our dangly carbon. Remember I said carbon number 6 is dangling out there? And that means that it's dangling for a reason so that it's sterically available to do some reacting. So this oxygen is available and it's sterically able to attack the phosphate of an ATP. There's a lot of tension when in these phosphates that are right next to each other. So what we're going to do is form a bond, and then we've phosphorylated. So this is a phosphorylation, and so we've activated this glucose by adding a phosphate group. This keeps the glucose in the cell. It stops it sufficiently charged enough that it's not going to get back through the permease enzyme. So it's going to stay within the cell at this point. But we're going to study this reaction next chapter when we take a look at glycolysis. It requires energy. And of course, it's controlled by an enzyme. And this is called a phosphate ester here. All right, so I've alluded to this before, but probably the most important reaction that we're going to talk about this semester, this chapter, is forming a glycosidic bond. A glycoside is where we've taken the OH on this anomeric carbon, the OH that's dangling off of it, and we replace the hydrogen with some carbon. Now the carbon can be in simple alcohol. It can be something crazy, and we're going to see how crazy it gets later on. But it can get really, really crazy. But we can see that this was now a reducing sugar, and since we have a carbon here, it is no longer a reducing sugar. So to tell whether you have a glycosidic bond or not, you take a look at your sugar. You find your anomeric carbon. How do you find your anomeric carbon? You look at the oxygen in your ring structure. As long as the CH2OH, the dangly carbon, is pointing up, then you look to the right. You guys need me to say that again? You look for the oxygen to find your anomeric carbon. You look at the oxygen in your ring. You look to the left of it. If the carbon number 6 or whatever carbon that is hanging off of your ring structure is pointing up, then you're going to look to the right, and that will be your anomeric carbon. Remember how we made this, right? We had the tree fall down and the back end of the tree curl up, and this is carbon number 5 that had the oxygen that nucleophilically attacked the carbonyl. Yes?
Will you ever see that dangling carbon coming down?
If I flip it over like a pancake, when we look at our disaccharides, you're actually going to see a situation where in order to draw it properly, it's going to be pointing down.
And then in that case, we just go.
You have to really think about it.
Okay.
You have to use your imagination and flip it over, or maybe turn your head upside down. So to deal with the case that the CH2OH is not pointing up when you look for the oxygen in the ring, and it's not pointing up, then you just flip it over in your brain. I'm not going to do that to you on an exam, all right? Especially not this first one. All right, so we're able to find the anomeric carbon. Once you find that anomeric carbon, you find whether you have an alpha or beta OH. Now, if your anomeric carbon is not carbon number 1, if you have a ketose instead of an aldose, you've got to make sure that you're looking at the right OH. Because we could have a case if this was a hexose, but it made a 5-membered ring because it was a ketose, then there could be a CH2OH pointing up here, and it still be a, let me, I don't want to confuse you guys too much, but if I had this case, this sugar, and this was just a CH2OH, and this was my aldehyde, I'm not my aldehyde, my ketone, it would so this one would attack this carbon. All right? And so you would have a 5-membered ring. This would still be your anomeric carbon. So we can see that if the carbon that is the anomeric carbon is carbon number 2, then there might be a CH2OH there. But this is still a free anomeric carbon because we find the anomeric carbon. You look for the OH that's attached to it. It doesn't matter if there's another CH2OH. CH2OH here. All right? There could be that. But because this is free, that's telling me that it's free to react. But we don't have that here. All right? That would be a 7-carbon chain. Okay, so what happens in forming the glycosidic bond is we're forming, what is the form here? What is the functional group that we're forming here? We have a carbon, oxygen, hydrogen, so this is an alcohol. And we're condensing it with another alcohol to form a what? Esters have a carbonyl. Ether. That's an ether. Very important for you guys to know, it's an ether. It's almost like a double ether because we have carbon, oxygen, carbon here. So that's an ether. And then we have carbon, oxygen, carbon here. Now, it doesn't just have to be a CH3. It can be any number of things. We're going to see that it's going to be another sugar ring. When you have the condensation, putting together of 2 alcohols, one being the OH on a anomeric carbon, and then the other being whatever you want. Whatever you want. Okay? Just another OH. Anything. If there's no hydrogen on the OH that is on the anomeric carbon, then you have a glycoside. So I'm going to give you a structure, and I'm going to ask you to circle the anomeric bond. The glycosidic bond, I'm sorry. I might ask you to point out the anomeric carbon and to circle the glycosidic bond.
We don't have to know the whole reaction.
You don't have to draw the whole reaction. What I'm going to do in this test is show you a structure. But you should be able to do it at this point. This isn't that bad. You're going to look and find that OH on the anomeric carbon and put together. You take away the hydrogen and you put together the group that's not the OH there. All right, so this is how we're going to link our sugars in disaccharides and polysaccharides. So here, if you look at this sugar, this monosaccharide here, you can see that this is an alpha, right, because it's pointing down. And it gets a little crazy here. An alpha because it's pointing down. And then it's not going to the anomeric carbon on this one. It's connecting to the 4th carbon on this glucose. So here we have an alpha 1,4 glycosidic bond. So this is how we're going to notate our glycosidic bonds. We're going to first say, is the OH on the sugar that has the anomeric carbon in the glycosidic bond, is that alpha or beta? So when you're naming these polysaccharides, disaccharides, when you're naming the bond, you first identify the sugar that is in the glycosidic bond. You find out whether the OH is pointing down or up, and that's what this alpha has to do with. So this is alpha because this is pointing down. And then you number it. First you number the carbon that is the anomeric carbon on the first sugar, and then you number the carbon that the OH has bonded to. So here, this is carbon number 1 on this sugar, and this is carbon number 1, 2, 3, 4 on this one. So this is an alpha 1,4 glycosidic bond.
You said it again. Yes.
Sure. So what you're going to do is first, in any to identify what kind of glycosidic bond you have, you first find the sugar that is in the glycosidic bond, that has the anomeric carbon involved in the glycosidic bond. So find that sugar. Second, you look and see whether that is an alpha or beta. So this one's pointing down, sort of, kind of. It's pointing down, so we're going to call that alpha. Then you number from the sugar, you find the carbon, you number the carbons that are involved in that glycosidic bond. You're going to first number the one that has the anomeric carbon involved, so that's carbon number 1 in this case, and then the other sugar. So this is alpha 1,4.
How do we know the other one's beta?
This one, we don't know if this is, this could be alpha or beta. It doesn't matter. We don't know anything about this one. The linkage here, saying alpha 1,4, says nothing about this OH, whether it's up or down. Doesn't matter.
I guess I'm just confused on the second one because I would say
Oh, I haven't gotten there yet. Let's just focus. Is everybody good on this one? Yeah? Okay.
Explain how you numbered the one to the right.
This one? Okay, so first I found where the anomeric carbon was, and I found whether this is going to be carbon number 1 or 2. This is going to be carbon number 1 because I don't see another CH on that one. So this is carbon number 1, 2, 3, 4. Just remember our tree going down. It's all going to come back to the tree. Don't ever cut down trees by yourself. Okay. We're just going to do it in our brain. Here, we're going to cut down the tree of our sugar. All right, let's move on to this one. All right, because this is from the textbook, and they wanted to conserve space. Okay, they're trying to say, okay, let's look for the one that the anomeric carbon is in. So we say this one because this is the anomeric carbon here. That's not in the glycosidic bond. So this one is the one that's in the glycosidic bond because we know that this is the anomeric carbon. All right, so this is their feeble attempt when they go bloop like that it was alpha because it's pointing down. Really what we should have done in space is push this up here. Okay, to draw this better, it would have been better to have this up here. All right, so here, if this were up here, and so they would be pointing down, so this would be alpha, because this is pointing down. It's our feeble attempt. Pointing down. Does everybody see that with a little J there? So it's pointing down, alpha. Oh, that's carbon number 1. What is it connected to on the other carbon? Carbon number 1, 2, 3, 4, 5, 6. So this is an alpha 1,6. Okay, you guys with me?
And as far as naming, that's all we need to know is like alpha 1.
Yeah, you got to name the bond. To name the bond. Yeah, there's other stuff I'm going to ask you to know. All right, now, this one's nuttiness. All right, this is actually wrong. What I want you to do is to correct this. This should just be down. Okay, so if you guys can correct that. There's no bloop there. This is just down. And we're going to say alpha down there. So there's two corrections. I could have corrected either way. All right, so if this is just down and it's connected to this one, then what do you notice that's different from up here? This one, up, our anomeric carbon is involved, right? So that's going to be alpha. Oh, wait a second. In my other one, the anomeric carbon's involved. Oh. So I have to say beta. You could do beta alpha, alpha beta. Doesn't matter. You pick one, right? You pick one. So then that one's beta. This is quite the awkward way to write this, right? Like that.
So you could call it alpha or beta.
No,
Or beta.
this one, yeah, the order doesn't matter right here to talk about the linkage, all right? So this one has to be called alpha because it's pointing down, the way I wrote it. This one has to be beta because the way I wrote it up here. And then it's connected at both in carbon number ones. So what they did to make it look better is this is the case where I flip this one over like a pancake. So from here to here, it's flipped. Because you see the dangly carbon? Can you guys do that? I find that some of the younger people cannot do this because they didn't play with G.I. Joe guys when they were little. They played with video games. Right? Imagination. You have to be able to like imagine things. So here, this one and this one are written the same, correct? But this one, I have it pointing down, but that's because this and this, it's just flipped over. Okay. Can you just recognize that? All right. Do you think I'm going to do that to you on the test?
So how do you know if it's beta? Is it because both the
No, here, I know that this is beta because look at this one. This is at the anomeric carbon. It's involved in the glycosidic bond, and it's pointed up. Right? Up means beta, down means alpha. So this is how we're going to put our sugars together to form disaccharides and polysaccharides. The important monosaccharides that I want you to eventually get is our glucose, our galactose, and our fructose. Oops. Our glucose, galactose, and our fructose. The glucose is the one that you are going to be immediately responsible for in this exam.
Dr. Bear,
Yes.
I have a question. The slide 23, why are we not also specifying D in the name?
Oh, we're just naming the bond. I'm not naming the whole thing.
Okay.
I'm just naming the bond here. So yes, you would, to name it properly, you would say D-glucose or whatever. Yes.
So for the beta, it doesn't necessarily always have to involve the anomeric carbon for the second ring.
For the beta, always has to be on the anomeric carbon, but the anomeric carbon doesn't have to be the first carbon.
Oh, okay.
Okay, like I showed here, that and here, the anomeric carbon doesn't have to be the first carbon. If it's a ketose, then it's going to be the second carbon. But that means that it's going to be, the first carbon's going to be dangling off. I haven't really showed in my slides that example. I just want to caution you. So here, up on here, we only had one anomeric carbon involved in the glycosidic bond. But in this case, both of them were. Now, I'm going to do a little foreshadowing. This one is, and these, which the top or the bottom would be a reducing sugar? The top or the bottom, which one will be a reducing sugar? What do you have to be a reducing sugar? You have to have a free anomeric carbon. The top. Yep, these are our free, quote-unquote, free anomeric carbons because the anomeric carbon has the OH on it. There's an H on the O that's bound to it. This is tough, guys, if you're taking vacations in your heads. And I can see by your faces a large population of you are off somewhere nice. Spring break is coming. Okay? Spring break is coming. So here, and this is the free anomeric carbon. Yes?
So that makes it a reducing sugar.
That makes it a reducing sugar because it can get oxidized there. So again, these are the, did I answer your question?
Yeah.
Yeah, okay. These are the sugars that I eventually want you to know the structures of. We're going to come back and look at those later. Glucose, I do want you to know. Fructose, look at that one. This is our example of a ketohexose. This is the anomeric carbon. I found the oxygen in the ring, made sure that the dangly carbon up to the left of it was pointed up, and then here. How did I know that it wasn't flipped over, that this was not the dangly carbon? There's got an OH on it. Very good, Sean. There's an OH on it. The carbon number 6, all right, is going to be pointed up off of the carbon that doesn't have an extra OH because this was the OH on it, right? Remember this. This is carbon number 5 in our structure. Carbon number 5 in our structure. The OH on the carbon number 5 attached to the carbonyl. So the carbon number 5 can't have another OH on it. This is it. So this is carbon number 1, 2, 3, 4, 5, 6. It might take some marinating for you guys. I knew that this was the anomeric carbon because there's both the CH2 and an OH. This is not the anomeric carbon because there's just an H on it. There's no OH on it. Both of the right and left off of this oxygen have a CH2. Which one is the anomeric one? It's going to be the one with the OH. Do you guys see that? Okay, a little tricky there. Fun with sugar. All right, and amino sugars. Oftentimes we're going to do some, and with sugars, it gets really crazy what happens with sugars. We're just going to do crazy stuff to it all over the place. But one of them is, I think the common name for this is sialic acid. But we take out an OH and put an amine or add groups onto the OHs, so it gets crazy. I saw these types of sugars in as components in our glycoproteins. So one of them, and I don't know for sure, but sialic acid, we had to test specifically when we were characterizing our antibodies that we made at Regeneron for sialic acid content. Because so you know that an antibody has the FAB and the FC portion, and the FAB is what interacts with the antigen. And the interaction is really all over this sugar is short sugar chains all over the structure. If the sugar chain had a sialic acid at the end, we were really jazzed because that would stop the liver from breaking down the drug. So we were looking at that. One of the tests that my group ran was to determine how many sialic acids per protein molecule that we had, and it had to be consistent. So one thing about making drugs is that the kind of drug that you made for the clinical trials, it has to be exact forever, or you have to go and do the clinical trials all over again. So the controls on making a drug are really, really tight. And it's very scary when you make new batches in a new building because things can be a little different. But we would make sure, we have to have 13 salicylic acids per molecule. So I remember doing high-performance liquid chromatography to determine that. But think recognition and when you look at sugars. All right, so sucrose, lactose, maltose, and cellulose. These are our common disaccharides. What I want you to know from these is which sugars make them up and what kind of bond holds them together. So here's the definitions of them. But really what I want to do is look at the next slide. So here's just a companion slide. So here is lactose. It's a galactose and a glucose. It has a free anomeric carbon. The galactose is this one here. And here it's a beta 1,4. Do you guys see that? Let's do some practice. This is the carbon number 1. We see this is the oxygen. Go to the right. You see carbon number 1. That's an anomeric carbon. It's up, so that's beta. It's connected to carbon number 1, 2, 3, 4 on the glucose. Some people do not have the enzyme to break a galactose glucose beta 1,4. Yes, Aaron?
If the glucose going down, why isn't that alpha?
The glucose, no, it's only alpha or beta if the OH on the anomeric carbon is pointing up or down. You only look at the anomeric carbon to determine if it's alpha or beta. So here, this is the anomeric carbon. It's pointing up in a weird way, but it's pointing up, you can see. And so that's going to be beta. So if you do not have this enzyme, you're lactose intolerant, and cheese pizza is not in your future unless you take the enzyme, right? Who takes those lactate enzyme pills? Some of you take those. Do they work? The tablets work better? So that's good. That's nice. They didn't have that like 10 years ago. So, or maybe they had it 10 years ago. Maybe I had a friend in grad school that had a hard time with it. And they tolerate yogurt because maybe the bacteria has it. I don't know. All right, we all have maltose. Glucose 1,4 this is starch or a disaccharide. If we continued this would make starch. So maltose is a 1,4 alpha 1,4 bond. So here, this is down. It's alpha. It's connected 1 to 4. So we just say HOH because we don't know if it's alpha or beta. It doesn't matter. Alpha or beta on this glucose doesn't matter. That's not what we're naming. All right, sucrose is glucose and fructose and an alpha 1,2. Now, what I want to point out to you guys is that I can show you these sugars and you can tell me what kind of sugar it is. Or if I ask you, sucrose, what are the sugars involved and what bond makes them up? I think that's fair. If I say sucrose, not show you the structures. How about if I do that? If I give you the name for this test, not for the final. Final might be more than that. But for this test, it's fair game for me to say the name and you to tell me which sugars are involved and what is the bond that holds them together. So for sucrose, it is a glucose and a fructose and an alpha 1,2. Cellulose is the disaccharide. Cellulose is the polysaccharide. But it's a beta 1,4. None of us have the enzyme that can break up a glucose-glucose beta 1,4. We don't. Who does? Who has the enzyme?
Cows?
Cows don't. They have friends, though, that live with them. In which stomach? Which stomach? I don't know. They have, how many stomachs do they have? 4? That's crazy. It's really, and then what do? They throw up in their mouth and then swallow it again.
Yeah.
They chew a little bit more and then it makes it to the second stomach. That is some crazy. You don't care. Just put it next to this. I don't really care about this one. All right. So, in some of these I said what the bonds were, but I want you to know the bonds for all of them. Sucrose, glucose, and fructose, and an alpha-1, 2. And lactose intolerant, you don't have the beta-1, 4 galactose glucose. No one has this. No mammal has this, but you might have a bacteria that helps you out with that.